In an earlier clip, we saw that the mean field approximation failed for describing the phase transition temperature for 1D Ising system. Here we will develop the exact theory for the 1D Ising chain, showing that the critical temperature is equal to 0, hence there is no ferromagnetism in one dimension. The solution has been found by Keson, actually here at Leiden in the 1930s. Let's consider the following system. Let's assume we have n spins, each of a moment sigma I, which can assume plus or minus 1. The spins are organized in a ring, meaning that spin 1 can interact with spin 2, and spin n can interact with spin n minus 1 and spin 1. Now the side energy, epsilon I, is given by h times sigma I plus j times sigma I times sigma I plus 1. Note that we now redefined the interaction energy such that only the energy to the right is counted for the side energy of spin I. Now in this situation, the canonical partition function reads as beta h sum on all spins I from 1 to n sigma I plus beta j sum on all spins I from 1 to n sigma I plus 1. Now, in order to make this situation symmetric, we add in the first term another term sigma I plus 1, and because of the double counting, we divide prefactor by 2. Then we have to consider the sum on all possibilities of sigma 1, sigma 2, sigma n, where each of those can have the two values plus or minus 1. Now we rewrite the equation by turning the sum in the exponent into a product on all spins I from 1 to n e to the power beta h half sigma I plus 1 plus beta j sigma I plus 1. Now let's have a look in the different values that the exponential factor can have. If we assume that sigma I plus 1 is equal to minus 1 and sigma I is also minus 1, we obtain a factor e to the power minus beta h minus j. For sigma I minus 1, sigma I plus 1 plus 1, we obtain e to the power beta j. Likewise, for sigma I plus 1 and sigma I plus 1 minus 1. For the last possibility, where sigma I and sigma I plus 1 are both 1, we obtain a factor e to the power beta h plus j. Let's describe this table that we just obtained as a matrix. The matrix is called the transfer matrix. Further, let's consider that we write the sigma i's as vectors. The vector 1, 0 describes a sigma I of plus 1. Vector 0, 1 describes the situation that sigma I is minus 1. Using these definitions in the products of the partition function, we see that now the partition function we can write as the sum on all the various possibilities of sigma 1 times the transfer matrix times sigma 2 times sigma 2 transfer matrix sigma 3 and so forth until sigma n transfer matrix sigma 1. The products in this expression are commutative, meaning I can place the brackets at any place I want. Let's put the brackets in between the two transfer matrices. Hence, Z now reads sum on all sigmas, sigma 1 transfer matrix times sigma 2 times sigma 2, and so forth. Now, since we have to sum on all different possibilities of sigma, this product in the sum is the identity matrix. Hence, we can neglect the identity matrix, finally leading to the partition sum is now given by the sum on sigma 1 equals to plus or minus 1, sigma 1 transfer matrix to the power n, sigma 1, which is nothing else like the trace of the transfer matrix to the power n. Hence, we transferred our calculation to a calculation in the trace of the nth power of a matrix. For that, it's easiest that we diagonalize the matrix, calculating the eigenvalues of the transfer matrix. Those eigenvalues can be found by determining the determinant of the transfer matrix minus the lambda eigenvalues times the identity matrix and equating this to 0. The equation will lead to a second-order equation in lambda, finally leading to lambda plus minus is equal to e to the power beta j cosine hyperbolic beta h plus or minus sine hyperbolic squared beta h plus e to the minus beta j. In our calculations, we use the expressions for the sine hyperbolic of x is equal to e to the power x plus e to the power minus x, and that cosine hyperbolic is equal to 1 plus sine hyperbolic. Now it's easy to determine the partition function of the 1D Ising ring, reading z of n, beta, and h is equal to the trace of the transfer matrix to the power n, which by diagonalizing is equal to lambda plus to the power n plus lambda minus to the power n. Further, we assume that n is very large, hence the letter sum is dominated by lambda plus to the power n. Given the partition function, we now can calculate the mean mechanization per particle if we assume the magnetic field is equal to 0. The mean mechanization per particle is given by 1 divided by n, 1 divided by beta, del log ln z del h is equal to 1 divided by beta sine hyperbolic from the derivative with respect of the cosine hyperbolic plus 1 divided by the square root times sine hyperbolic times cosine hyperbolic coming from the sine hyperbolic squared in the square root times the internal derivative of times beta. We see that this is proportional to sine hyperbolic beta h, which for h equal to 0 is equal to 0. Hence, in 1D, there is no phase transition and the critical temperature is equal to 0. Having now the exact solution, we can look for the dependence of mechanization or other observables of the system as a function of the parameters, which in this case is, for example, temperature or the interaction potential. Here you see what happens if we change the interaction potential J from either -1 to 0 to +1. We see that the mechanization changes its steepness depending on the interaction. Likewise, we can calculate from the partition function the spin-spin correlation given by the mean value of sigma I times sigma I plus r, where r is the distance of the spin. Those correlations drop off exponentially with distance, with a typical correlation length zeta. From our exact theory, we can calculate this correlation length as partial derivative of the log of the partition function with respect to j, and find that at high temperatures zeta is extremely small, hence there are no correlations, but by lowering the temperature, the correlation length steeply rises. At temperatures close to the phase transition temperature, zeta will be very large, hence there will be large correlations in the spin values, which we neglected in the mean field approach. The transfer matrix trick can be extended to 2D. That has been achieved by Lars Onsager in the 1940s. He found for the 2D Ising model an analytic expression for the partition function and found that for the 2D system, kBTC is given by 2j divided by log of 1 plus square root of 2. What happens can be easier viewed in computer simulation. Here you see 3 panels of a Monte Carlo implementation of an Ising model where spin up is characterized by a white pixel and spin down characterized by a blue pixel. At high temperatures to the right, we see a complete random orientation of the pixel. If we lower the temperature close to the phase transition temperature, we see that large ordering takes place in this 2D place. The correlation length gets larger. If we are well below the phase transition temperature, there are very large correlations, and the system finally will freeze to a homogeneous orientation, either all spins flipped up or all spins flipped down. You should run the simulation yourself in order to visualize what is happening in this 2D system. The link to the program you will find on Brightspace. We have developed here the exact Ising model for a 1D Ising ring. We confirmed that the critical temperature is 0 for the 1D system. In the exact models, in 2D, Tc is given by 2.269, and in 3D, it's 4.512. The latter is a simulation result, since an exact solution of the 3D Ising model is still not found. For n dimensions higher, the mean field solution is the exact solution of the problem. Now, in statistical physics 2 and also in statistical physics in the master phase, the Ising model will play an essential role to extend to more general theories of phase transitions and the connection of phase transitions with symmetries and dimensionalities of the system.